Okay, so we're going to talk about a lot today, or in this particular video, about limits. So we're going to be able to use the properties of limits. We're going to be able to evaluate one-sided and two-sided limits, and we're going to be able to evaluate limits involving infinity. So there's going to be a ton of limit stuff today, or in this video. Okay? We've already talked about this definition. The limit as x approaches a of f of x equals L means that f of x arbitrarily gets close to L as x gets close to some number a, but not equal to it. We've already talked about that. So when you find a limit, okay, we're trying to find here the limit as x approaches 1 of x to the third minus 1 over x minus 1. Now, we cannot just simply plug 1 in, because if we did that, we would get 0 over 0, and that would be bad. So, how could I get x minus 1 out of the denominator? Well, let's see. So I have the limit as x approaches 1. Now, x to the third minus 1, that's a difference of cubes. So, I'm sure you all remember how to factor a difference of cubes. So I'll just write this here. Okay, so I factor the top. What happens? The x minus 1's cancel out. So I have the limit as x approaches 1 of x squared plus x plus 1. Okay, now it's safe to plug in 1. So our limit is 3. Okay, now another thing you could have done, you could use the graph to figure out what the limit is, or you could use a table in your calculator, okay? Or you can just do it like this, kind of do it the algebraic way. This would be the algebraic way, okay? So there are several properties of limits, and basically if you have a sum of two functions and you're taking the limit, you can take the limit of the individual functions and add them together. Same thing with subtraction, multiplication, a constant, division, powers, okay? All that stuff you can do for limits, okay? So for example, it says, you will learn in example 10 that the limit as x approaches 0 of sine x over x equals 1. Use this fact along with the limit properties to find the following limits. So part A, okay, we have x plus sine x over x. Well, what we can do is we can rewrite this. We can do x over x plus sine x over x. Okay, so I can take this and split it up into two fractions. Well, I have the sum of two functions, so I can write them as the sum of the limits. So the limit, now x over x is just 1, okay, plus the limit as x approaches 0 of sine x over x. Well, the limit of 1 is just 1, plus, now this information up here is very critical. We know that the limit as x approaches 0 of sine x over x equals 1. So we can put 1 in there. So our limit is 2. Okay? So we're just using limit properties. Now, that's our first example. Now I have to erase all this. Now next, we have the limit as x approaches 0 of 1 minus cosine x squared, or cosine squared x, I should say, over x squared. Now, here's what we have. Now, guys, they're giving us this information because they probably want us to use that limit at some point in the problem. So if you look at 1 minus cosine squared, if you remember your trig identities, you will remember that 1 minus cosine squared is sine squared. Okay? Well, That is the limit as x approaches 0. Now wait a minute. You see this here? Okay. We have a function squared. We can do the limit of that squared. So in other words, I can do the limit as x approaches 0 of sine x over x squared, right? Because the sine and the x are both squared. Well, that's 1 squared, which is 1. Okay? So, again, we're getting the limit of sine x over x involved. Now, if you look at C, I'm like feverishly pressing this button. That helps me erase all this. So C, okay, what we have is we have the limit as x approaches 0 of the cube root of x, or cube root of sine x over the cube root of x. Well, that's the same thing as the limit as x approaches 0 of the cube root of sine x over x. But we can do the third root of that entire limit. But we know that the limit is 1 here, so it's the cube root of 1, which is 1. Okay, so just by knowing that limit that's given, if we can get our functions in terms of that, it makes our lives a lot easier. Okay, also we're using limit properties. We're using those. Now, to find limits by substitution, okay, so here's what we have to do. Okay, so we have the limit of a quotient. Okay, so that means I can do the limit, excuse me, as x approaches 0 of e to the x minus tangent x over the limit as x approaches 0 of cosine squared x. Okay. Now, that equals, now we have a limit of a subtraction here, right? So we have a limit as x approaches 0 of e to the x minus the limit as x approaches 0 of tangent x over, now this is cosine squared, correct? So now I can take that whole limit as x approaches 0 of cosine x and square it. Now, as x approaches 0, what does the graph of, now you can do the graphs of all three of these functions, and look what happens as x approaches 0. As e to the x approaches 0, as x approaches 0, we are approaching 1, because e to the 0 is 1. Tangent of 0 is 0. Cosine of x, or excuse me, cosine of 0 is 1. So 1 minus 0 over 1 is 1. Okay? So all we're doing is we're splitting, what we're doing with the properties, guys, is we're splitting these up into individual limits. Okay? The individual limits are a lot easier to find than this whole thing taken together. Okay? All right. So here I go, erasing again, feverishly tapping my iPad. We're approaching 10 minutes in the video. I'm trying to keep this limited, but I have limited space, so I must improvise. Got it. Okay. So we're going to do the same thing in part B. Okay. We have the limit as n approaches 16 of the square root of n divided by the limit as n approaches 16 of log base 2n. Okay, well, plug 16 in for n in both limits. So I get the square root of 16 over log base 2 of 16. Well, the square root of 16 is 4. The log base 2 of 16 is 4. So 4 divided by 4 is 1. So again, another example of splitting them up into individual limits, find the individual limits, and then do your operations. One-sided and two-sided limits. Basically what that means is we're going to find the limit as x approaches the number from the left side and then the right side. So this would be as x approaches just some arbitrary c from the left, and this would be as x approaches c from the right. So that's what a left-hand limit and a right-hand limit is. Okay? So when it says here, find the limit of f of x as x approaches 2, and then this minus sign up here means from the left. Okay? So this is the key. Okay, now as x approaches 2 from the left, that means we're coming from values less than 2 up to 2. So this would be my left-hand limit. So as x approaches 2, I plug 2 in to this piece right here. Whoops. So that is -4 plus 8 is 4, minus 1 is 3. So that's the left-handed limit. Okay? Now, the right-handed limit, so x approaches 2 from the right, which would be the 2 and then the plus sign. Now we're approaching from numbers greater than 0 or greater than 2. So this is going to be our right-hand limit. So now 2 is going to go in here. So 2 times 2 minus 3 is 1. So we have two different limits, and that is dependent upon which side you are coming from. We are approaching the same number, but we're approaching 2 from the left, and then we're approaching 2 from the right. Okay? So as you notice, those two limits are different. We'll talk about how that works here in a second. Okay? Now, here's sort of, this is what this is describing. So the limit as x approaches c of f of x equals L if, and only if, the left hand and right hand limits equal L. So in other words, the left and the right hand limits have to be the same for the overall limit to be that number. So in other words, in this example, okay, there is no limit because 3 doesn't equal 1. We approach 2 from the left, and we approach 3. We approach 2 from the right, and the function approached 1. So they're approaching two different numbers from either side. So that would mean there would be no limit for that. Okay? Now, at a point of discontinuity, it says find the limit of f of x as x approaches 3. So, find the limit. Now we're going to do x, let's see, limit of, as x approaches 3, of x squared minus 9 over x minus 3. Now we're going to use this piece because x doesn't equal 3, it's approaching 3. So this is for when x is not equal to 3. Well, if I plug 3 in right now, we're screwed. But if I factor the numerator, x minus 3, x plus 3, the x minus 3's cancel out. Now we can plug 3 in, so our limit is 6. Okay? So as x approaches 3, that graph approaches 6. Now, there's a discontinuity at 3. It says right here, basically, that f of 3 equals 2. All right? So 2 does not equal 6. So F.
Please pardon the interruption. Again, we will have AP testing next week.
You hear this?
On Monday, we will have about 25 students in the library. And announcements, once again, will be in the morning before 8 a.m. Thanks, Ms. Joyce, for all that you've done with the AP testing. Have a great day, and go Rebels.
By the way, nobody heard that because the building is empty, just for the record. But good luck on your AP test next week. So F is discontinuous at x equals 3 because the limit as x approaches 3 is 6, but the actual value at 3 is 2. So those aren't equal, so it's discontinuous. The greatest integer function, okay, this is the graph of the greatest integer function. It's a step function. Find the limit as x approaches 3 from the left. So as x approaches 3 from the left, we are up here of the greatest integer of x. So as x approaches 3, we are on this branch right here, and our limit is 2, okay? Because y equals 2 as x approaches 3. Now, here's the other issue. Now let's approach from the right. So if I approach from 3 to the right, now we're up here on that branch. Well, that limit is 3, okay? So the limit as x approaches 3 from the left is 2. The limit as x approaches 3 from the right is 3. So the limit as x approaches 3 of the greatest integer of x does not exist because 2 does not equal 3. Okay? So the left-hand limit and the right-hand limit must be equal. If they're not, there is no limit overall. Okay, so now x approaches infinity. So as x approaches infinity, we have functions that approach a certain number. Same thing for negative infinity. This basically is our, well, I shouldn't write that. Okay. These are our asymptote rules. Okay. This is what we did when we did asymptotes. Okay. Now, let's look at this graph. It says let f of x equals sine x over x. Find the limit as x approaches infinity of f of x. Okay, so here's our function. We are approaching negative infinity, or approaching positive infinity. What's happening to the graph? It's getting closer and closer to 0. Okay, so what happens as x approaches negative infinity? What happens to f of x? Well, here's our graph. Same thing happens, right? We are getting closer to 0. All right? So again, that's just going to infinity and negative infinity. What's happening to the graph? It's getting close to 0. Now, what happens here? Find the limit of 1 over x squared, or x minus 2 squared, as x approaches 2. Okay? So let's do 2 from the left. Okay? So we're approaching 2 from the left. So here's the graph. As x approaches 2 from the left, what's happening? It's going up. So the limit is infinity as x approaches 2. What happens when we approach 2 from the right? Okay? Well, we're approaching 2 from the right. What's happening to the graph? Oh, it's going straight up. So it's infinity again. Now, when both limits equal infinity, or negative infinity for that matter, the limit does not exist because you can't count infinity as the same thing. What it does mean is that there is a vertical asymptote at x equals 2, which makes sense if you think about it. Okay? There is no value at x equals 2. There is no value. So there is an asymptote. So when both limits are infinity, you're going to have an asymptote, not a normal limit. Okay, last one. So the limit as x approaches 0 of sine x over x. So if I approach from the right, what's happening? We're going to 1. I approach from the left. Oh, we're going to 1. So, since both the left and right-hand limits are the same, the limit of sine x over x as x approaches 0 equals 1. Okay? So that's limits. 20 minutes, I know, but it's easy. It really should not be that hard for you guys. Hope you enjoyed the interruption, the announcement that was made to no one. I'm sitting in an empty school, so enjoy your weekend.